Good morning, everyone. I'm Julia, part of the editorial board of Build Up. Build Up is Europe's largest international portal for energy efficiency in buildings. It is a unique community that provides the opportunity to discuss, contribute, and collaborate with other experts. Build Up aims to bring together stakeholders working in the building sector. Our editorial work is organized around the topic of the month, which allows us to go deeper into a specific theme. Each month, several items are produced, such as overview and technical articles and infographics, and so on. Build Up also offers the opportunity to host webinars on all the topics related to energy efficiency. More recently, Build Up has opened the opportunity to interview experts in the field to share their knowledge in front of our cameras in the Build Up Expert Talks. Build Up portal shares daily the most relevant news, publication, events in the field of energy efficiency and renewable energy, but also participates actively in many European events around the year, such as EPP Center and Riva conferences, H2020 Interreg and Cost Action events, Covenant of Mayors, and much more, with the aim of further disseminating the results and helping to create high-quality media content. Build Up content is updated daily, reaching around 120 new items each month. But Build Up is not only us. Build Up is a community, and we invite you to be part of it. So by becoming a member, you can contribute by uploading your own content and promoting your own news, events, or publications. Build Up will help you to reach a broader audience through our social media channels and newsletter. So it is a pleasure to host today's webinar entitled Practical Tools for the Construction Sector in the Digital Twins, which is organized by the EU-funded COGITO project. I leave now the floor for the introduction of the webinar and the agenda. So thank you for your attention and enjoy.
Welcome everyone to COGITO's project webinar, which will be focused on our tools, which we are developing during 3 years of project duration. So first of all, for the introduction, we will present our innovations and goals in the beginning of the webinar. Then we'll move to the first poll, which we will ask you to answer 2 questions, a very short poll, so don't worry about it. We will see all the results just afterwards. Then we'll move to quality control data acquisition and the tool which is related to this area. And our colleagues will also present the geometric quality control tools and visual quality control tool as well. In the end of the very deep knowledge of this webinar, we'll move to Digitaire as well as Digital Command Center. You will be also you're also welcome to answer to reach the answers from our speakers and to ask questions. So I hope that these questions will also raise during the whole webinar. And the second poll also in the end will be displayed to get the feedback from you if all of these tools are answering your needs. In the end, we'll wrap up the whole discussion and give also you some conclusions. So I would like also to introduce Yorgos, who will present COGITO project innovations and goals.
Thanks, Agnieszka, for the introduction. So let's start a bit with the COGITO project as an introduction to the project. And COGITO, in a nutshell, to the best of our knowledge, the digital twin community has so far overlooked the construction phase. And although many European member states have not yet initiated the digital transition in construction, still waiting for clear demonstrations of its tangible benefits. The use of building information models and modeling has risen over the past years, mostly to facilitate the communication, collaboration, information exchanging, and enabling process improvements, focusing though on the design and planning phase. So it comes as no surprise that going beyond the static BIM, lack of commonly agreed standards and low interoperability among collected data during the construction reveal a major drawback to enterprises' digital transformation. Even for large construction enterprises with full access to state-of-the-art digital reality capturing tools. So there is a clear need to go beyond static building information modeling, and going beyond static building information modeling requires it requires leveraging technologies like IoT, cloud computing, and artificial intelligence. Furthermore, construction projects require collaboration between many parties. Thus, there is need for transparent platforms capable to handle digital data from different sources. The literature is a breast of examples of applications that can benefit from the use of digital technologies, BIM, and smooth exchange of data. Examples like progress and resource tracking, automated quality assessment, dynamic prediction of resources requirements, to name but a few. These exemplary applications, as well others yet to be convinced, highlight the need of a construction phase digital twin model named COGITO. A digital twin model that encapsulates all the mechanisms to share the data across stakeholders, enabling this way the development of new solutions and services for the smart construction of buildings and infrastructures. Such a digital twin model must always be compliant to standardized methodologies for data management. And actually, this is what COGITO targets to solve, with the aim of minimizing construction project durations and costs, and reduce workplace accidents. COGITO aims to perform a semantic alignment between novel data capture techniques and construction digital twin applications by introducing methods and technologies to ensure interoperability. Interoperability among the different components that are applied within, let's say, a digital twin platform, the core of the entire tool chain. Value-adding end user services are to be delivered for the timely detection of health and safety hazards to humans, construction quality deviation defects, as well as up-to-date workflow management to minimize construction project time and cost overruns, and alleviate workplace accidents. At this point, I'd like also to highlight the balance of COGITO consortium, comprising 13 partners from 7 member states who bring significant expertise and capacity in their respective domains, as well as existing tools that are being adapted, configured, and repurposed for the needs of the project. So if I could rephrase what was presented earlier, COGITO conceptually introduces a digital twin methodology that combines as-planted data along with as-is information, data acquired on field on the construction site, and analyzes such data in a semi-automated way to minimize the construction project duration and cost, and reduce workplace accidents in the construction industry. by developing and delivering a bundle of services that facilitate the timely detection of health and safety hazards to humans, support the timely identification of quality defects and deviations, and provide means for real-time workflow management on site. Methods and technologies to ensure interoperability among the different components compromising the COGITO architecture are applied within the COGITO digital twin platform, the core of the entire tool chain. Last but not least, I'd like to mention that COGITO also deploys graphical user interfaces like the ones that will be demonstrated today, and apps to interact with the construction stakeholders and issue alerts to crews on site. To deliver its scope, COGITO has set 4 technical and 2 business exploitation and knowledge transfer objectives. The first one to deliver a technical objective is to deliver a construction digital twin platform that fuses the as-designed nth dimension BIM data with as-is visual data and big data streamed from IoT sensors to produce a live digital representation of the construction site, enabling this way updated remote visual inspection of ongoing works by construction stakeholders. The second objective is to alleviate construction projects costs and time overruns through the delivery and validation of vertical digital tools for quality control and workflow management based on data retrieved from the digital twin platform to facilitate this way immediate detection of discrepancies or deviations from the construction site. The third objective, technical objective, is to effectively reduce construction site accidents through the development and delivery of digital tools for health and safety management applicable in design, planning, construction phases. The fourth objective, technical objective, to demonstrate the overall COGITO solution on actual construction sites to quantify the benefits of the proposed tool chain, evaluate the COGITO application's acceptance by construction stakeholders, and obtain feedback for improvements. The first business exploitation and knowledge transfer objective to research, design, and promote the data exchange formats that facilitate the interoperability of the construction digital twins with future evolutions of the building information model to relevant standardization bodies. And finally, to promote the adoption of the COGITO solution through intense dissemination and knowledge transfer of the project outcomes toward the targeted stakeholders, reaching out to audiences within and beyond the European Union. Today, we are presenting the quality control services and relevant user interfaces, starting from with the visual data preprocessing module, responsible for acquiring the data required as input for the quality control components, the geometric quality control and the visual quality control services to semi-automatically detect deviations and defects of erected construction elements, and finally digital and DCC for visualization purposes of the quality control results. And that's it for the introduction of the COGITO project. I'll pass the floor to Agnieszka with regards to the first poll that we mentioned before.
Yes, we have 2 questions in the beginning, just to know your background, so we can move to the first question. What do you know about digital twin? We just want to know what is your background? Do you have the knowledge already? And do you have maybe a practical experience with digital twin? So please vote. If we have already the answers, we can, I think, move to the next question. What do you know? Now we have the answers here. So most of you know the concept. That's very good, as we will be getting into the details in the remaining part of the presentation in the webinar. And the second question is, in which context do you know of digital twin in the built environment? I hope you have had a chance to already answer the questions. Sorry, what are the results of the poll? Now, 59% of you have heard of digital twin in the context of asset operations, so it's very good, and asset construction as well. So it's very, very well. I think we can move now to further presentation, and I will give the floor to Tanas.
Hello, everyone. So one of the first tools responsible for entering the data into the COGITO system is the Visual Data Preprocessing Toolkit, which is responsible for uploading the visual data that can be collected through various data sources and devices we saw in the previous slide by Yorgos. So we have multiple sources like drones, cameras, laser scanners, etc. And all this data can be entered into the data processing toolkit in order to be processed and become available to the other tools of the COGITO system. Now, all this data, when it comes right from the camera, are raw. So in most cases, they need some pre-processing, so cropping, filtering, etc., in order for them to be passed on to the quality control algorithms, the geometric and the visual quality control tools, respectively. Now, the architecture behind this is like this. So basically, the visual data preprocessing tool gets the data from the various sources, and after that, they are processed and tagged, and along with their metadata, they are passed on to the digital twin platform, which then makes them available to all the other tools of COGITO. And specifically here, we are talking about the quality control tools, which are separated in the geometric quality control and the visual quality control tools. So regarding the visual data acquisition, as I said, for the two-dimension data, basically images, we have different cameras, infrared, RGB, etc. smartphones, HoloLens head-mount displays for augmented reality, which can act also as capture devices, drones, etc. And on the other hand, for the 30-point clouds that capture the as-built status of a building, we have laser scanners. Now, the workflow is like so. Basically, the user of the visual data preprocessing tool follows these steps. First, they select the construction project they are working on, and then based on this project, they get a list of the different work orders that have been defined during the construction, and some of them will contain a list of IFC. IFC is the Industrial Foundation Classes, which is a 3D representation of the BIM model of the building, along with different data for each element of the building. So we get the IFC elements that we need to check for quality control. And based on this, the user then uploads the necessary files to the visual data preprocessing toolkit and associates these images or laser scans or whatever with the relevant elements in the building. Finally, this metadata, along with all the preprocessing that is done to this data, is passed on to the digital twin platform, and they become available to the quality control tool appropriate for the job. Now, regarding the use case of the geometric quality control, the user first scans the required IFC elements using a laser scanner and provides, as you can see here on the right, the 3D scanned model of the building. And then these are uploaded as an E57 or a PLY format file using the visual data preprocessing toolkit front end. They are assigned the capturing timestamp, and then they are forwarded to the digital twin platform. On the visual quality control side, a photograph of the required IFC elements is associated with the element. The metadata is goes along with the image in question. Some processing is performed if necessary, for example, cropping an image or filtering some element, and then they are uploaded to the digital twin platform as well. Now, the image processing side, as I said, involves cropping, resizing, Gaussian blurring, contrast modification, or brightness modification. These are additive, so a user can select one or all of these to perform on its image. And here we can see an example of how this works in practice. Yes, you can start the video, please. Now, first, the user signs in with a Keycloak account that is the same throughout the entire COGITO platform. And using these credentials, they are presented with this screen, which is the selection of an existing project, and the project corresponds to the building that we are talking about. So here we have a demo of a school building, and we have different work orders here defined through another tool of COGITO that has some quality control activities ordered for this building. So one of them is a geometric quality control task, and it involves, in the example here, these 5 elements within the building. One is a column, stair, a slab, a wall, or a railing. You can see here the name on the left, the IFC ID of the element in the middle, and the type of entity on the right. Now, after the IFC elements are selected, the user can upload files that correspond to this particular element. And here you can see an example of multiple files that can be associated, either PLY or E57 format. And for each one of those, the user can select the timestamp from when this was captured, so to signify what stage of the construction this corresponds to. Now, when these are selected, they can be saved locally first and then uploaded to the digital twin platform as well. Now, regarding the visual data for the visual quality control, in this use case, the user selects the visual quality control task from the work order. And then, based on the elements involved in this work order, Again, we have a column, a stair, a slab, and a wall here. We can select which ones are involved in this photograph that the user will be uploading. And the user can select an image from the computer, upload it, and then go on to perform some processing on this image. For example, select cropping, selecting a default, let's say, aspect ratio, and then manually assigning a specific range of interest on this image. And you can see on the right a preview of what the image is going to be, and then maybe apply a filter or modify the contrast of the image in order to make it easier for the algorithms to work with this image. At the end, these are saved again and uploaded to the Editor Tool platform. Here you can see another example. In this one, of course, we are now talking about demo data. We are not talking about a construction site. We're just demonstrating all the activities that can be performed. Here the user can see, for example, a frame of a door and how this is mounted, for example, on the wall, and if the mounting has some errors performed in that. Now the size can also be changed in the final file to make it a bit more systematic. And then all the files after processing are uploaded, as I said, in the Digital Twin platform. Finally, another capability that we will demonstrate here is now this was a manual uploading of data. The Visual Data Preprocessing Toolkit also has the ability to add specific devices that are IP cameras that you can access through a static connection and have a periodic work order assigned to them. So every X amount of hours, days, or whatever, daily, weekly, or a one-time operation, assign a job to capture and perform specific preprocessing to all the images that are captured from this device. For example, you can have in a construction site an IP camera set up in a specific location and looking at a specific set of IFC elements, wall, columns, etc., and assign this camera to take a photograph every day to map what changes have been performed. And based on this data, then the Visual Data Preprocessing job can be operated on these images. And this concludes the demonstration of the Visual Data Preprocessing Toolkit. I will pass on the floor to Agnieszka.
Thank you, Dennis. Thank you for your presentation. Now we will move to geometric quality control for automatically controlled geometric quality against defined specifications, which will be presented by Martin Bueno from the University of Edinburgh. I would like to encourage you all to raise questions if you have already some, and we will then read all of these questions and answer in the end of the webinar. Martin, I think the floor is yours.
Thank you, Agnieszka. Hi, everybody. So I'm going to talk about the geometric quality control that we do in the COGITO project. So first of all, we are going to start with you already seen this slide. So this is going to show which elements are going to be combined during the quality control, for example. And what we do is we combine the 3D geometry in the design phase and the schedule for each of the activities that we have. So for example, when those components are going to be built and when they are going to be finished. And then we combine it with the 3D scanning of the reality that's built. And we mix them together, we do some computation, and we perform the quality control of it for later be able to visualize them in different good GUIs or other support apps like augmented reality or in your computer. So the first part is we divide it in two. So is the planning and then the execution of it. So during the planning stage, what we need to know is from the as designed BIM model, and it's a 4D because it's containing the schedule of it, apart from the geometry and the materials and all that relevant metadata information. We process that to extract the different quality controls needs that we need to comply during the project, and most importantly, when. So after processing it, we are going to get a list of geometric QC tasks that are going to be verified during the construction phase. So, for example, where do we get those quality control checks that we need to do? So we have different sources. The most standard one comes from the rules or specification or regulations or norms of the different countries, but it also can come from project-specific or user-specific ones. So, for example, if your client requires to check or have a more constrained threshold for the curvature or the deviation between columns, you can put it there, and we can analyze it with that threshold instead of the ones that are on the regulations. So in this case, I'm going to show you these ones are coming from the concrete regulation, and it's an ISO standard. So all those values are coming from that rules. So you can see here are different rules that will need to be checked during the construction. But these rules are also specific for different elements. So for example, walls, columns, or slabs, or beams, or the rails for the steel cases, and etc. and etc. So when you analyze the BIM model, you can extract the different rules instances that you need to check for each of the elements. So each element will have a type and a material, which is going to be linked to the rules. So those rules, we are saying there are a dictionary of rules, or QC rules, or QC dictionary, whatever you want to call them. They are going to store some metadata. So every time that we go to the BIM model, specifically using the IFC file, we see that element and we say, okay, so this element is a column, for example, and is of concrete. We need to verify all these different rules. But there are some rules that require more than one element. For example, location between a column and a beam. So if the position between them there is okay. So in that case, you need to query for both of them. And that requires some relationship between them. So for example, if we go to this IFC or BIM model, we know that we have all those elements, all those different elements. So the beams, columns, walls, and slabs. And from the rules, we identify these 4 or 5 different relationships between them. So we have the stack of the columns and the walls. The physical connection is mainly between the beams and the columns. Storage adjacency, so it's like one slab on top of the other, and horizontal adjacency between the beams and columns, for example. So in this project, example project, we identify that there are this number of relationships, which means we are going to need to extract a lot of QCs from here. So, but also we started a graph that looks like this, where you can see each of the elements. So each node is an element of the building, and each arrow is the relationship between them. So for example, the red ones are columns, and the blue ones are beams in this case. And you can see there are some beams that are connected to the columns, which are touching between them, and then you have the columns that are one on top of the other. This is only for visualization, and it can be useful for people if you want to explore it, because you can identify key components that are, if they are not complying all the QCs, the geometric QCs, it might have an impact in the future of the construction or the stability of the building. So, but what is important from these relationships and this graph and the rules, we obtain a number of different QC rules that we need to verify during construction. So for example, from the dictionary that we have of 15 rules, we know that we need to comply this number, almost 10K of different rules during the construction, which is a lot. We are pretty sure that nobody is going to inspect them, all of them. But if we do it automatically, we can certainly verify at least most of them, a huge number of them. So this is only on the planning. But what happened during construction? So during construction stage, we need to combine that list with the as-built data and run an automatic algorithm to do the checking. And so what we need to do is check which of these rules instances are pass, fail, or cannot be controlled because we don't have enough data for it, and why it's happening. So for example, we have a building, and in this case, we're going to use a laser scanner because it's more accurate. But in the future, we cannot outrule other sources like photogrammetry or the scan robot or drones, which are going to be faster in acquiring the data. Or you can combine most of those technologies to be faster, for example, or have a more accurate data. So what we do for checking these rules is mainly do a matching between the elements and the design, that's build data and the as-designed data that's coming from the BIM model and the TLS. And we obtain the as-built pose of those elements. So we can use that pose to check the different geometries between the differences and the tolerances between the as-built and the as-designed data, and the values that are on the rules. So I have a couple of examples. So in this case, we have a column and a beam this is the mesh that's coming from the as-design. And we know that we need to verify this QC instance, which relates to, if you can see here, it relates to QC number 12 from the dictionary. And this is the component that is involved. This is, for example, this is a beam, and it refers to the inclination of the beam or slab. This metadata that we can fine tune it, or we can change the values there so the user can see more, is more visual interest for them, or the information is more relevant for them and they can understand it. So also we know that this rule has to be checked by this date. Of course, we know that there are some delays and that can change, but originally it was coming from this date. So for future stories that are coming in the future, we don't need to verify this because we are going to have the relationships, and we know that the rules the instances are there to be verified, but not at that moment. So if you analyze this one, so in this case, we introduce a small deviation in the inclination of the beam. So you will see here that the beam has a bit tilt. This is the as-built data on the point cloud, and then the mesh, or the 3D design of it. And when we verify it, we see that the result is a fail. So it's not complying the tolerance that the rules are saying, which is 0.5 centimeters, and in this case, it's almost 9 centimeters of inclination. But this element also was connected to the column. So it contains another QC instance, which is this one, which we see that we have two components in this case, and the rule refers to QC5 in the dictionary, which is beam to column location. But because it was only an inclination, we see that the connection between them is not going to be affected, but the point cloud is affected only on the vertical axis. And in this case, it was a path. And see that the tolerance was 2 centimeters and the difference is only 1. So, and also we have the timestamp when we perform the QC. So the quality control staff and the project manager, they can see when these QC rules were verified, obtain a report of it with more detailed information to pass it to the different authorities or the clients. And that's mainly the geometric quality control. So Agnieszka, up to you.
Thank you very much for your presentation. And now we'll go back to Thanos from Sarah's crew. He will present visual quality control for automated defect detection in pictures acquired on site. So I think Thanos, the floor is yours.
So for the visual quality control, this involves the automated visual inspection and defect detection based on 2D images. So the data is coming from, for example, satellite images, unmanned aerial vehicles, and they are combined with scheduling for the visual quality control inspections through the digital twin, and then we can perform the quality control inspection and visualize also the results in different user interfaces. Now, what are the quality control needs that be conducted regarding the visual quality control? So basically, based on the elements involved in the construction, we distinguish between the two different materials, two different categories. Basically, these involve concrete defects or steel defects. And for example, here we can see some of the defects that we can detect regarding concrete construction elements. For example, cracks, blistering, honeycomb, efflorescence, or holes present in concrete. Regarding the steel surfaces, the algorithms that we employ can detect defects, for example, rail track damages, pitted surfaces, patches, scratches, and things of that nature. So let's go to the use case. So as Martin said earlier, we have the planning stage, and then we have the construction stage, and then we need to check against what has been planned and what has been constructed. Basically, we select the different IFC elements involved in the work orders of the quality control. And then on top of that, we can perform a detection using deep learning algorithms working on the images that we saw before. So the different results can be no defect detected or a fail and the defect was detected with some confidence, or if the confidence is a bit low and we are not really sure, we can declare an undefined result of this activity. So we have an unknown surface material state. So this is an example of what the algorithm performs. So you can see here an annotated image with a crack detected and the confidence of 0.92, which means we are 92% sure that this is actually a crack. This corresponds, for example, to an IFC element seen here, a column, and the report that comes out of that is, as you can see here, the global ID of the element, the material was selected as a concrete, and the predicted label, which is crack, and the confidence level, which is 92%. All this is then, along with different elements of the COGITO project, are passed on to different user interfaces. One of these interfaces is the DigiDAR, which is the on-site augmented reality-based digital twin information visualization and decision-making tool, which is an application running on HoloLens devices. And the scope of this tool is first to visualize the results of the quality control components, both the geometric and the visual. Second, to visualize potential construction and site hazards for health safety issues. And finally, to collect as-built data as part of the visual data preprocessing tool that you saw earlier, acting as a capture device, basically using the camera of the HoloLens head-mount display. Now, regarding the architecture of the visual data preprocessing, the visual quality control tool, basically we take the images coming from the visual data preprocessing toolkit. As you see here, the elements coming from the digital twin platform, the work orders coming from the WODM tool of COGITO, and based on this, we can provide within DigiDAR a 3D AFC viewer, so the user can see the 3D model of the as planned building. The 2D visual data coming from the visual data preprocessing toolkit, so all the images that have been captured for a specific element. It can act, as I said, as a raw data collector itself, and then it can also generate, based on this data collected, a data preprocessing job, and finally demonstrate and provide the user with a confirmation user interface for the reports coming from the quality control algorithm. So the user can use Digitar to say that this is, yes, actually a defect or not. Now the workflow works like this. So as I said, the BIM model and the QC results are coming into Digitar, which is used first to visualize the BIM model and the QC results on site on top of the elements. And then for each of these QC results, the user can confirm or as well add some remedial tasks involved for them to fix the defects that we are confirmed. The process goes like this. The user first logins to the application, they select the construction project, and then they select the quality control mode, visual or geometric. They receive the IFC model and the QC results from the data platform. They can perform the registration of the 3D model onto the real world construction site. And then they can view the geometric and visual quality control results on top of the physical building. And finally, they can confirm or reject the quality control results and add the remedial works. This is an example of how the 3D model is demonstrated within Digitar, and the quality control results are demonstrated in this kind of user interface reports, where you can see the quality control rules, timestamps, description, distances, scalar results, and tolerances regarding geometry control, quality control results. And for the visual quality control results, the user can see the image as it came from the quality control, visual quality control tool, along with its annotation and the confidence level and the type of material the detection was based on. And on the top here, you can see that for of the past quality control result, you can see a blue annotation on the visual on the building, and for failed quality control, the user can see a red annotation. We can go on now to see a demonstration in video format, and you can see how this works on the HoloLens device. Yes, if you can start the video. So, first of all, again, with the same credentials as before, the user logs into the system, into the COGITO system. They can select the project, and they can select what type of activity they will perform: pre-processing, quality control, or safety control. In the quality control here, they can select to visualize the model on top of the building, overlaying the actual site. Here is of course not a construction site, but demonstration area we have in CERT. And they can have all the visual quality control activities that we performed attached to all the elements. And you can see here the red color here indicates some quality control results that have been with a fail result. And the user, as they go around, the model is registered to the actual building, and it follows the physical space. Now, the blue color results here indicate elements with the past quality control result. And the user can also, as you will see, select to view only the results and not the building itself as a BIM model. So this makes it a bit clearer. So it doesn't have too many cluttering elements on top of each other. And alternatively, the user can only see the 3D elements that are involved when the user looks at them. So here the user looks at this column, so it's highlighted, and an outline, green outline comes on top of it. And here, when they focus on the door becomes highlighted. It seems the video has stopped. Or is it me? Agnieszka, can you hear me? Agnieszka?
Yes, Manos, the video is stopped for me as well.
Video has stopped.
Yeah. Can you try and see if you can restart it from the middle? Yeah. Okay. So
It's fine.
okay. So yeah, it skipped a bit. So basically, we'll skip the part where the user can see the report. If you go to the middle of the video on the bar first, you can see the report where the user selects the QC result. All right, so the user can tap onto this. Okay, the user can tap on a result and see what is the result of this quality control operation. You can see again here the crack, 2% sure, and this is the result as an image on the right. And then they can also see the original image that was taken from that location before the preprocessing. And they can also confirm or reject the result and say, yes, this is actually crack, or it's not, it's a false positive. And they can also request remedial work to be performed on this element, basically fixing the crack, filling the voids, do a rebuilding task, set a priority and the time schedule. And they can add this task into the process of the construction. This was for a visual data preprocessing, a visual quality control operation. Now, as you saw, the past results are like this, so no defects were detected in this particular element. Again, this is a visual quality control result. And the user can confirm that this is actually correct. Now, here is a geometric quality control tag, and the user can select it as before. And here you see the different type of results coming from the geometric quality control process. So description, result, but also the different tolerances and the type of result for the measurement. Again, the user here can create remedial work for this. And this is most of the functionality that we have so far implemented in the tool, the digital user interface. Thank you.
Thank you, Tanas. Now we quickly move to Digital Command Center, which will be presented by Yorgos as the time is passing by. So Yorgos, the floor is yours.
Thanks, Agnieszka. Actually, I've realized that we are a bit behind schedule, so I'll try to keep it short. DCC, actually, DCC is a web application for off-site digital information visualization of the digital twin platform data. Actually, DCC, the Digital Command Center, aims to support the project managers on monitoring the construction progress, resource allocation, detected quality control, discrepancies and defects, safety measures and detected hazardous areas through visualization and navigation of the 5D asphalt data, construction and resource allocation data, and other data and annotations generated by the relevant digital twin applications. In this slide, we see the high-level architecture of the Digital Command Center. The COGITO Unity library is a collection of C# scripts, and it is delivered in the form of a Unity package. Actually, the COGITO Unity library is composed of 5 main components. First, the IFC to mesh generator client, which actually invokes the IFC to mesh generator servers to convert the IFC file to geometry, metadata, and material files. Although not part of the COGITO Unity library, the IFC to mesh generator is considered as an external framework that serves as the data transformation service that receives as input an IFC file and generates the geometry, metadata, and material files that can be used by clients like the one represented here. The mesh importer component provides the functionalities required to import geometry metadata and material files, and if needed, convert the IFC files to geometry and material files. Then the authentication management component, which actually implements actually it implements the OpenID connection logic supported by the digital twin platform authentication service, Keycloak in our case. The project management component responsible for communicating with the digital twin platform and obtain information about the available projects and the project data files, and the real-time data management component, which actually regularly sends requests to the digital twin platform to receive data generated by the health and safety, quality control, and workflow, and IoT location tracking data based on predefined schedulers. In this slide, a screenshot from the digital command center environment illustrates the main parts of the user interface, including the element tree view, the element properties, the navigation bar, the camera widget, the overlay selection, and the status bar. And I'm going to analyze a bit each of them further. The element tree view actually provides a hierarchical view of all elements in the BIM model, and allows the user to show or hide the elements that they choose. Each item in the tree view has separate show and hide buttons. By clicking actually the eye or the cross eye button displayed here. The default, actually regarding the grouping of elements, the element tree provides two modes of operation. The default mode groups all elements according to their position in the BIM hierarchy. While the alternate grouping mode is by element type. As we see here, for example, different elements are beams, building, columns, etc. The filter selection of DCC controls provides two types of filtering: the schedule-based and the box-based. Here is the schedule-based and here's the box-based. With regards to the schedule-based, the user has the option to filter the displayed elements by a date range and the time range taken into account during the filtering can either refer to the as-planned data or the as-built data of the elements. The box filter allows the user to focus on a particular area of the construction. Clicking the box icon enables box filtering and presents the users with a cube and the controls to move the face of the cube. The user can move the faces to contain the area that they are interested in, and this way the digital twin application will hide all elements that are not included in the box. To perform Okay, it's working now. To perform a more precise camera adjustments and movements, such as full top down or side view. A camera widget is available on the digital command center user interface. And actually, the camera widget represents the three axes defining the 3D space as well as a middle box. And clicking on any of them, colored axis, on any of the colored axis arrow, the camera orbit is moved fully to the axis edge. Concerning the different digital twin application results, health and safety, quality control, and work progress, but also the IoT location tracking data. The DCC user interface implements different overlays, different boxes for its overlay. And actually, the overlay selection buttons represented here allow the user to enable or disable its available layer. These are the 4 layers available corresponding to the data generated by the quality control services, the health and safety services, and work progress services of COGITO. Concerning the IoT location data overlay, it allows the tracking of entities capable of moving around within the construction site, such as humans or heavy machinery and equipment. The available entity types, groups, are retrieved dynamically by digital twin from the digital twin platform and are displayed with different colors. The work progress overlay colors the elements of the beam according to the construction progress. And there are 3 possible colors for the moment implemented for each element. The red color illustrating components whose construction has not started yet. Yellow, which represents construction of elements that are whose construction is in progress, and green elements whose construction has been completed. The very last slide, sorry, is about the geometric quality control results displayed in DCC. And I'll ask, if possible, to run the video that we have prepared. I didn't provide any information about the process that we follow to log in, etc. Actually, here we are displaying the results that were presented earlier by Martin. Colored red, the elements that were failed, and green, the elements that whose quality control has passed. And that's all from my side with regards to DCC. And I will be happy to answer questions. But at first, I would like to run the second poll. So, Agnieszka, the floor is yours.
Thank you very much. Yeah, the second poll is consisted of 2 questions, and we would like to ask you if what we presented answer your needs and will be needed in the future, and what do you think about it? So I think we can display the first question. Yeah, regarding today's presentation, how do you assess the tools presented? That will be really insightful for us. Also to organize the second meeting with you also through the webinar, because we are planning to organize more webinars about our tools during the next year. Hope you had already a chance to vote. I think we can see the results now. So I know what we can answer already. If they would be hard to integrate with current practice, I think we can answer that in a question and answer session in a minute, how we can do this. And now we can display the second question. Would you like to be kept updated or involved in COGITO? As I said, we are organizing also a few more webinars during the next year. So you will be also invited and informed about these webinars, about our tools that we developed during the COGITO project. I think we can see the answers already. Perfect. That's a good news for us. That's a good feedback for us. So thank you very much for your contribution, for your answers to our polls. Now we can, I think, move to question and answer session. We have a comment from Maciej Musiałek. He's asking about the sharing the video, as he would like to show it to the surveyor. I think, yes, I can answer already this question. Yes, we can share the video. It will be uploaded to our YouTube channel, as well as the whole webinar, which is recorded, and also will be uploaded to COGITO's YouTube channel. So you will be able to go back to all of these videos and all of the presentation. Maybe you would like to share it with your surveyors or business contact or wherever. Yes, so if you have some more questions, then please, now is the time to ask our speakers for more details or more information about the project. So if you have already the question, please do so. One question is that when will the project end, and how will the application will be available, and if it will be a package of applications or they will be maybe available separated. I think we can ask Yorgos as the project coordinator, and I think Yorgos, you can answer this question as well.
Yes, thanks, Agnieszka. Actually, with regards to the project duration, actually, the project is going to end in October 2023. With regards to the question about how we're going to deliver the different innovations introduced in the project, actually, we're targeting to have different bunches of tools targeting to different digital twin applications. For example, today we presented just the quality control services and how components are being integrated to make this happen. But we have other innovations that are relevant to other domains, like the health and safety. We're planning to have a targeted webinar for the health and safety components as well, but also the workflow management and monitoring. But at the end of the story, as I mentioned in the very beginning of the webinar today, in the middle of the overall solution, we have the digital twin platform. Unfortunately, we didn't have the chance to present the specific component functionalities today. Actually, I'm really satisfied with the progress that we have on this specific component. And we are planning to have, for sure, a targeted workshop for the digital twin platform as well, illustrating how data from different sources and different domains could be linked in an automated way and following standards that exist. I don't know if I answered all the questions.
Yes, there was one more about energy efficiency, how the tools will influence on. How do you think it will influence in that case in front of the energetic crisis and so on, and how does it influence the costs maybe on site? Some of speakers would like. Yeah, Oregos?
Yes, I can start, and maybe either Fred or other colleagues could contribute as well. As we mentioned earlier, the project focuses mostly on the construction phase. So although we are targeting to deliver projects that minimize costs and time overruns, we slightly investigate the energy efficiency as well with regards to materials management, but not that on that much detail. So I have not a clear answer yet, at least with regards to the impact that we're going to have in the energy efficiency.
Thank you, Yorgos. Do you have any more questions? If not, because we are behind the schedule, it's already almost 12:15. From my side, I would like to thank you all for your attendance and for raising some questions to us. And thanks to all of the speakers for today's presentation. From my side, I would like to encourage you to follow our website, cogito/project.eu, and also to join our social media channels and to follow them to be just updated with all of our tools and how the project is developing and what we are going to achieve. So thank you very much for your attendance today, and hopefully we'll meet during another webinar which we'll organize shortly. Thank you very much and have a nice day.
Thank you all. Bye.
Bye bye.